So I thought of another way of testing my quantum gravity hypothesis, and this is by using lasers in the vacuum and trying to see if any light from the lasers is scattered by the vacuum itself. And I've just been Googling around this topic, trying to find some kind of research that may support this conclusion and so on. And trying to find any precedence for this idea, and this is what the AI overview says. So it says laser scattering in a vacuum is a phenomenon where extremely intense laser beams interact with the vacuum itself, causing light to scatter, diffract, or generate new light. This occurs because the vacuum is not truly empty, but is filled with fleeting virtual particle-antiparticle pairs that can be polarized by the laser's strong electromagnetic fields. This effect, predicted by quantum electrodynamics, can be thought of as photons scattering off each other by briefly converting into these virtual pairs. So, I don't believe in particle-antiparticle pairs. I think that the phenomena of antimatter can be explained by the particles of the standard model that we have at the moment, such as positrons. I think positrons are probably W plus particles tunneling through the background, and but to be very quickly reabsorbed by the background in exchange for a photon. So we can therefore have positron emission tomography. I don't believe that matter is spontaneously created and destroyed as current physics does. I think it's highly unphysical to invoke particle-antiparticle pairs. And I think what's really going on is that if you get a powerful enough laser, and shine it through space, it will scatter off the electrons in the background of space, since my quantum gravity model predicts that tunneling electrons in the background mediate the force of gravity. They're responsible for instance, the scattering of light from different objects, and the trapping of light around certain objects, and the changes in the paths of light around objects also, as in gravitational lensing. And yeah, this could be a very good way of testing for my quantum gravity idea. I think if we use powerful lasers in space and try to see the same sorts of behavior that we see in lasers traveling through different media on Earth. So, for instance, if you get a laser and it travels through a block of glass, all the light from the laser is bouncing off the molecules in the block of glass. Hence, we can see the laser traveling through the glass because the light travels through it, then bounces off it towards our eyes, and so on, and we can hence see it. And the same is largely true, or very often true, of lasers traveling through the air. Sometimes we can't see lasers traveling through the air. If they're not powerful enough, we can't see them. It needs to be really quite a powerful laser beam for it to be scattered off air molecules and head towards our eyes. So, and really, what we need in space to detect this effect from uh, light tunneling from gravitational electrons is we need a very powerful laser indeed, to be able to see the light bouncing from electrons in the background and hitting our eyes. But the effect is still the same. It's still basically the same as a laser beam traveling through a block of glass. The laser light is always bouncing off of electrons. Um, the same is true of it traveling through air and water as well. It's always bouncing off an electron bound to an atom, and then it hits our eyes. So, because electrons in my model would be a lot more diffuse in space, they would be a lot more spread out, diffuse, less concentrated in given regions of space than they are on Earth, because, in spite of the fact that we can't see them, we're surrounded by electrons in the air. Um, so we, have a very sort of interesting medium in which to study physics terrestrially, and without invoking vacuums and so on. And yeah, we can observe all sorts of phenomena that's caused by the scattering of, for instance, light from different particles and electrons, really. And yeah, we can observe things that way. But this is, yeah, just one more way of testing for my prediction. I think I would predict that with a strong enough laser in space, it would be visible ultimately, and we'd be able to see the light being reflected from particles of the background, these background tunneling electrons that I talk about. And it would travel towards our eyes and we'd be able to see it like a normal laser beam in space. And yeah, I think that the particle antiparticles pairs business, I think it's highly unphysical. I really don't see it being the truth. I really don't believe in antimatter at all. I think antimatter can be explained using the particles of the standard model that we have at the moment. I think quantum gravity is going to necessitate us having to cut the standard model in two and get rid of all the antimatter. And I think, yeah, there's nothing particularly wrong with just invoking the particles we have at the moment in the standard model without antimatter to explain the physical phenomena that we observe in nature. And I think via Occam's razor, it's a much better model to invoke, thinking about things that way, not multiplying entities beyond necessity, not invoking assumptions that we don't need in our models. And yeah, I think quantum gravity is going to force us to do that in the end when we realize that the background is behaving in a very electrostatic fashion or in a very quantum electrodynamical fashion, if you like, and that it really is light bouncing off electrons in the background. And background electrons really have all these different behaviors whereby they can tunnel to within very close to an atomic nucleus, exchange particles with that atomic nucleus and draw the atomic nucleus towards another object, and hence we have this action at a distance in gravity. And yeah, I received an objection to my quantum gravity theory um, based on Rayleigh scattering, was it? I think someone was talking about how they saying that somehow in space there should be Rayleigh scattering going on because space is filled with tunneling electrons. Therefore, you'd see the scattering of light from different objects. And I think like Rayleigh scattering only goes on in the atmosphere, of course, because I think it's caused by light scattering from ozone very high in the atmosphere. And it favors the scattering of blue light for various reasons that it does. I'm not an expert on Rayleigh scattering, but it doesn't happen in space. And I was trying to make this point. And yeah, and I also brought up this idea of eclipses. Seeing an eclipse, we do actually see light scattering from different objects. If you think of an eclipse, you've got to think of the moon and then this gravitational electron density surrounding it. Then the moon passes in front of the face of the sun, and we see the light going off in all different directions, very much like a sunbeam. This is how this behaves. The sunlight goes off in all different directions because it's being scattered by the moon's electron density, and we see it scattering and some of the light coming towards our eyes because we can see these, like in the same way that we can see sunbeams, because we can see that a beam of light is traveling towards the earth, but we can see it, so it must be getting scattered from the air molecules towards our eyes. So in exactly the same way, when we observe light being scattered in an eclipse of the sun with the moon, we see the light traveling through the electron density of the moon, and it scatters from an electron in that electron density and hits our eyes ultimately on Earth. So we see these kind of beams of light around the moon when there's an eclipse. And the reason for that is because, well, it's nothing to do with the moon's atmosphere, is it? Because the moon doesn't have an atmosphere. Well, it has a very thin atmosphere of hydrogen and helium, but it's not really to do with that either, so much as it's to do with just the gravitational electron density surrounding the moon. So I still think that my idea is correct. I still think it's the most likely explanation for gravity. And yeah, I thought I'd just talk to you a little bit more about this avenue for potentially testing my idea, potentially thinking about electrons in the background and how they would be behaving under different conditions, and the sorts of scattering that we might hope to see from laser beams in the vacuum if they're very powerful lasers. And yeah, the sorts of experiments we could potentially set up to try and test for this model. So yeah, that's one thing I wanted to talk about. I think it's much more likely that electrons will be scattering this light as opposed to particle-antiparticle pairs. I'm a bit iffy about this idea also of photons interacting with one another. I don't think that we see a hell of a lot of photon-photon interaction in nature. Um, and I think photons can enter superpositions with one another very easily because they're governed by Bose-Einstein statistics, which allow for this to happen. And the superpositions of photons can get very, very large, I think, before they ultimately break. And I grant you, I think that there must be some level of photon-photon interaction, but I don't think we'd necessarily be observing it in laser beams quite so much in space. I think it would be more like the light is getting reflected from background electrons, and we know that electrons have this behavior, of course, because electrons in various media that we can study on Earth, such as air, water, and glass, we can see light bouncing from electrons in those media quite clearly, and we know it couldn't be anything other than electrons causing these scattering phenomena. And we do, to some extent, albeit to a more limited extent, see these scattering phenomena in space with things like eclipses. So I wanted to talk about that today, and hopefully I haven't bored you too much with my explanation. And yeah, hopefully I'll see you all soon. Thank you very much for watching. Bye bye bye. Love you lots.